All right, so now we're going to consider the case where there is no horizontal asymptote. And the reason that that's happening is because if you look here at the function in standard form, the numerator, as x goes to infinity, is going to be much larger than the denominator. So as x goes to infinity, this whole function is also going to go off to infinity. So that could be in a number of directions as it heads up. So we're going to see if we can figure out exactly where that asymptote is that it's headed towards. And I encourage you when we're finished here to look at a graph of this, to type this into Desmos so you can see what's going on. Before we get into the slant asymptote, let's go back to x-intercepts, holes, and vertical asymptotes. And the way we find those is by rewriting our function in factored form. So the numerator here multiplies to -2 and adds to -1. So the factors are x plus 1 and x minus 2. And the denominator is already factored as x minus 3. And that means we're going to have x-intercepts at -1, 0, and 2, 0. Since we don't have any factors that divide to 1, we don't have any holes in this scenario. The vertical asymptote is the value of x that makes the denominator 0, in this case if x were to be 3. So now let's see what happens with this slant asymptote. To figure out what happens with the slant asymptote, we're actually going to divide these two polynomials. And the reason we're going to do that is because we want to see, well, let's divide first, and then I can kind of explain where that's coming from. So this is a quadratic divided by a linear. And we know that they don't have a matching factor, so we can't just factor and get rid of something. But since we know it's a quadratic and a linear, a quadratic is the product of two linears, so we're just going to have a box. If we're using the division with the area model, that's 2 by 2. If you prefer one of the other methods that we learned, you're welcome to use it. I'm going to stick with the area model. So I'm going to say that one of my factors was definitely x minus 3. And my product is x squared minus x minus 2. So I know that this first box here is always x squared. It's always your first term. That means that the factor starts with x. I can then multiply and get -3x here. In order for this to be negative x, since this is -3, this would have to be 4x. Oh, I'm sorry, that's incorrect. This would have to be 2x. Since 2 minus 3 will give you -1. So once again, that's a 2 right there. So I put the 2 up here. 2 times -3 is -6. Now that's not correct because I want it to be -2, which means I must have a remainder of 4. 4 minus 6 gives me -2. So the answer to this division problem, which is another way of writing h of x, I'll write it over here, is that h of x is equal to this divided by this, which is x plus 2, with a remainder of 4, and we can put the remainder over the divisor. So that's what we used to do with the remainders way back when we did long division. So this is the quotient that we got. This leftover part still needs to be divided. All right, so that's what we have now, x plus 2 plus 4 over x minus 3. So now let's think a little bit about end behavior again, since we're thinking about an asymptote. As just this little part right here, let me circle it, just my remainder, just this last term, as x goes to infinity, we're going to have 4 divided by infinity. So as x goes to infinity, 4 over x minus 3 is going to go to 0, which means as x goes to infinity, we can ignore this whole thing right here because it's just going to be 0. So therefore, as we zoom out and x goes to infinity, this function is just going to look like the line x plus 2. So the slant asymptote here is going to be the line y equals x plus 2. So to summarize, in order to find a slant asymptote, you take your original function in standard form, you divide your quotient here without your remainder. You can kind of just ignore the remainder, becomes your slant asymptote. And the reason you can ignore the remainder is that because when we're thinking about asymptotes, we're thinking about end behavior. So we're thinking about x going to infinity, which means that this remainder will be headed to 0.